a little bit of a resume. Who is Hossein? Hossein started his PhD in 2006 to be completed in 2009 at the University of Nantes on electromagnetic characterization of composite materials. Then in 2009 to 2011, he was professor at the University of Nantes. From 2011 to 2015, he was professor at the French Naval Academy, a military school. From 2015, he's at the University of Lorraine in a research group on electrical energy of Nancy. So working on energy and superconductivity. I'm going to give the time to Professor Hossein Menana to present his talk today on electromagnetic control and characterization of conductive material. Thank you.
Thank you, Frederic, for this introduction. Dear colleagues, dear students, buenos dias. I'm very pleased to be here for the first time at the University of Mexico, and I would like to thank Dr. Frédéric Triot, who invited me to give, with the support of the University of UNAM, to give this talk on electromagnetic control and characterization of conductive material. This is a part of my research work at Lorraine University. In the following, I will begin by a short presentation of my research group before moving to the scientific part of the presentation, in which I will describe the context of characterization of conductive material. I will give a review of the main method used for the characterization of material in general, with a focus on electromagnetic methods, in particular eddy current testing, in which I will try to explain the basis principles. And then I will end the presentation by some works we have done in this domain in the last 10 years. My research group is called GREEN. It is an abbreviation of Groupe de Recherche en Énergie Électrique de Nancy. Nancy is a town located at northeast of France. I don't know how to use this. At the frontier with Belgium, Luxembourg, and Germany. It's about 400. Sorry. I spoiled it. It's about 400 kilometers far from Paris. It is under the tutelage of the University of Lorraine. We are, it's relatively a small lab. We are about 51 persons, including PhD students. Since January, we have a new director, who is Professor Nordin Takurabe, who succeeded to Professor Bernard Ava. The main research topics are electromagnetic actuators and electrical machines, dynamic behavior of electrical system, including power electronics, electrochemical sources and energy storage systems, and modeling characterization of superconductors, which is the specificity of our lab compared to other labs in France. In the works concerning superconductors, we develop models, loose models in HTS, high temperature superconductive tapes, and bulks for their integration in power system, mainly in particular electrical machines. Several configurations of inductor. Of superconductive inductors have been developed in at a GREEN research group. I will not develop this configuration, but if you have questions, I can answer. I will answer if I have. We have worldwide collaborations, including collaboration with UNAM University, represented by Dr. Frédéric Triot. Let's move to the scientific part now of the presentation. What I mean by characterization, we want to characterize the physical properties of materials and their structural properties. Physical properties concerning new materials, such as composite materials or new alloy. We have to know their properties to integrate them in numerical modeling, for example. So we have to characterize them before. And for structural geometry, it's a test quality control. We can measure thickness or characterize flows. It's a local characterization with keeping the integrity of the tested material. So that's what we call it NDT. A non-destructive evaluation when it concerns physical properties, and non-destructive testing when it concerns the geometrical properties. Several methods are used to characterize materials. The most common one is ultrasonic testing, given this figure. It's an ecography. We realize an ecography of the tested material. It's a pulse echo method. We create ultrasonic waves in the material, and we use the different echoes to characterize thicknesses, velocities of acoustic waves, or even eventually a defect to a flow. We use the time of flight of the acoustic waves as well as the magnitude of the echo we receive. As the air constitutes an infinite impedance acoustic waves, we have to use a couplant, a gel couplant, between the transducer, which is generally a piezoelectric transducer, and the tested material. Sometimes we use honey. Honey is a very good transmitter to acoustic waves. To overcome this constraint, when the tested material is conductive, we can also use electromagnetic acoustic transducers. We induce directly acoustic wave in the tested material by using electromagnetic forces. We use an EMAT. The transducer is called EMAT, electromagnetic acoustic transducer. It is constituted of a radio frequency coil, generally serpentine coil, and a DC, a permanent magnet. The radio frequency coil will induce eddy current in the tested material at the surface, since we work at high frequencies. The combination between the eddy current and the static magnetic field will create ultrasonic waves that will propagate in the tested material. Another method used is liquid penetrant testing to characterize surface cracks in materials. It's a very simple and low-cost method, but it's very messy, and the tested material have to be brought to the workshop and to put it under the test. In this method, we begin by cleaning the tested piece, and then we spread on it a particular liquid. We wait a certain period until the liquid penetrates the flow, so the cracks, by capillarity effect. We clean again the material, and then we spread a developer on it. The developer will absorb the liquid that penetrates the cracks, and then we have a map of the cracks on the surface of the materials, of the tested material. We have radiographic testing. It's like radio we use in medicine for bone fillers. We put a tested material between X-rays and a developer, and then we can detect an eventual flow in the material. Thermal infrared testing, we hit the surface of a material, and then with an infrared camera, we can detect the presence of a flow, since the thermal properties change with the presence of a flow in the tested material. There are other techniques like visual inspection, laser, label leak testing, and other one, which I will not develop here, but you can find information about this method in the web. Move forward. I put here all the magnetic and the electromagnetic testing methods. I begin by magnetic particle testing, in the left. Here, when it concerns cracks on magnetic materials, we spread a liquid loaded with magnetic particles on the surface of the material, and then we apply an external magnetic field. The magnetic particles will fill the cracks to reduce the reluctance of the material. So you can get a map on the surface of the tested material formed by the magnetic particle, which sometimes can be detected by direct visual inspection or special light, UV light. Okay. To apply an external magnetic field, you can use a yoke or leads electric, put an electric current on the material. The first method here, magnetic particle testing, concerns external flows or cracks. When it concerns buried or far, how my English is, when it concerns buried flows, internal flows, you can use what we call magnetic flux leakage method. When you magnetize the material, it concerns magnetic material, ferromagnetic material. You magnetize the material. You apply a magnetic field on the material by a yoke, and then with a Hall sensor, you can detect a flux leakage due to the presence of flows. This is called magnetic flux leakage inspection. Of course, we have when it concerns conductive material, we have the 4-point measurement to characterize the conductivity or even the presence of flow locally. And the most common one is eddy current testing. In eddy current testing, we have a coil, a sensor which is generally a coil fed by an alternating current. This coil will create an alternative field. If you put this coil above a conductive plate or near a conductive plate, the alternating field created by the coil will create eddy currents in the tested piece or tested sample. This eddy current will create their own file that will oppose the primary file, the source file created by the coil. That will result in a change of the impedance of the coil. This change of impedance will be used to characterize the properties, the electrical and geometrical properties of the tested material. Why? Because the eddy current created in the material depend directly on the electrical conductivity, the permeability, and even the thickness of the material. The presence of a flow, an eventual flow in the material, will deviate the current in the material, since the current cannot go through the flow. This deviation, this deviation will result in a change of the repartition of the magnetic field and the environment of the coil. That will introduce another change in the impedance. So we made a correlation between the impedance change of the coil and the geometry and the physical properties of the tested material. This is the basic principle. go forward. We have two main modes of operation. We can operate in frequency domain, so that we sense the impedance variation of the coil. And we use an impedance plan response of the coil. We have here the proper impedance of the coil in air. Sorry, it's very sensitive to. We have here, we start from the self-impedance of the coil in the air, and then when we put the coil above a material, if the material is ferromagnetic, the impedance will vary this way. We go this way. This is the effect of the lift-off. What's shown here is the typical responses of an eddy current sensor above a material. If it's ferromagnetic, it will go here. The presence of crack will induce a variation in this direction, and the presence of the conductivity will lead to a diminution of the reactance, because the eddy currents will oppose the source magnetic field, and then the reduction of the coil. So we go down here. If the tested material is conductive, we go here. For example, here the response for aluminum. If we put the coil above the aluminum, the presence of crack will give a response in this direction, and the variation of the conductivity of the tested material will be in this direction, in this way. These typical responses. We can also work in the time domain. So the coil will be fed by a transient voltage or current, and then we use the response, the current variation in the coil. We generally use the current variations, the current above, when the coil is above the tested material, minus the current of the coil in the air. So we use the variation delta E. Here, delta V. For the characterization in this case, we use the peak value, its time of occurrence, the zero crossing time, or this second peak here. This are used to characterize the properties of the tested material, or even the presence of a flow. We have two main configurations of probes, which we call absolute probes and differential probes. In the absolute probes, one coil is used for the excitation. One coil is fed by an alternating current. The same coil can be used to sense. Same coil can be used to sense the result for sensing, or you can use a secondary coil for sensing, or you can measure directly the magnetic field instead of measuring the induced voltage on a coil to characterize the material. And in the differential probes, we have two coils wound in opposite directions. A differential probe is made of two coils wound in opposite directions, so that we sense here the variation of the impedance. We eliminate directly the self-impedance of the coil. We consider only the variation of the impedance due to the variation of the physical properties of tested material, or an eventual presence of a flow. You have here a typical response of a differential eddy current probe. I can, if you have questions later, I can explain more if you want. I have to speed up the. The apparatus you can find experimental apparatus. It's a simple impedance analyzer, since we are interested in variation of the impedance of the test of the coil, or an industrial portable apparatus. The probes, we have different type of probes in geometry, different size, sub-millimeter, from the sub-millimeter to centimeter. The detection is based on synchronous detection to get the active and reactive part. You have an oscillator that creates the frequency, the basis signal of excitation, which is amplified to feed the sensor. You sense the difference here as a differential sensor is put there, differential coil. You sense the variation of the impedance, then you made across a product with the measured signal here with the reference, and the reference shifted by a quarter of a period. So you get these signals here, there, this one and this one. You put it through a filter to remove these parts to keep only the mean value. So you get the active and reactive part, real and imaginary part, if you like, and then you display it in an impedance plan. Okay. Eddy current testing has several advantages. It is a non-contact testing, which is very important. A clean testing, you have not two extra products to put. It's portable testing, so you can achieve an in-situ testing without interrupting the process. It's very important. It's a rapid and a rapid testing, but it has its limitation as every method. It's used only for conductive materials. A defect that does not affect the eddy current flow will not be detected. Flows that are parallel to the surface will not affect eddy current, since eddy currents are parallel to the flow, so that they will not be detected. Complex geometries like edges or corners are difficult to characterize. We have to a careful interpretation is necessary, since many parameters affect eddy current, in particular the liftoff. A little variation of the liftoff will give you a completely different variation of the impedance. So you have to know if the impedance variation is not due to this this probe moving, or sorry for, and skin effect. You have studied skin effect, eddy current, since we are in frequency domain, alternating current. The eddy current flow only in the, or 60%, 63% of the eddy current flow in the skin depth here, given by this equation. The skin depth is inverse proportional. Yeah, inverse proportional to the conductivity, the permeability, and the frequency. Yeah. So sometimes to saturate the material, we can add a static magnetic field to saturate the material, and then to go deeper in the tested material. There are many applications, industrial applications to eddy current, like conductivity measurement, thickness, very small thickness measurement, or coat measurement. When we measure the coat, for coating measurement, the coat do not need to be conductive. The coat, if it's not conductive, it acts like a liftoff, and the liftoff influences the impedance variation of the coil. So we can measure a non-conductive coating on material. rapid railway inspection, pipelines, oil and gas pipelines inspection, aircraft fuselage, rift-in fuselage inspection, and heat exchanger tubes control. In this case, eddy current is, in my knowledge, the only way to characterize defect in such systems. I put here an example of tube inspection, heating steam generator tubes, inspection of steam generator tubes in nuclear power plant. Here is a synoptic or picture of a nuclear power plant. You have the primary, you have the primary circuit here, in which primary liquid circulates. It circulates in the, it floats in the heat exchanger tubes or steam generator tubes here in a closed path without contact with the external secondary path, in which we create steam here to rotate turbines to create electrical energy. These tubes are submitted to harsh environment in terms of thermal gradient and mechanical vibration. So they have to be controlled periodically. And the eddy current is the only mean to control these tubes here. If a flow is detected in a tube, it is clogged. It is clogged on both sides here. So if many tubes are clogged, the heat exchanger will be removed and replaced by another one. Okay. Here I put figure. This figure represents typical defect or typical flows that may occur in this tube, and the typical response of absolute and differential probes here. An absolute here and differential here. I don't know if we have internet. I have an applet too. We have not internet. Okay. For scientific issues, what we do in research in this domain, we look for new approach for characterization, generally a mixing of method, eddy current with ultrasonic testing, for example, or inductive thermal inspection. We test new materials, like composite materials, sizing and optimization of eddy current sensors in terms of topologies and performance. We have to develop advanced inversion data techniques, since we do not limit to the detection of the flow. We have to characterize the flow in its geometry, depth, size, and so on, to make decisions whether we continue to we let the material to continue in its functioning, or we remove the material. And this inversion technique needs generally systems learning, which needs modeling. It's generally 3D modeling with several constraints in multi-scale dimensions, non-linearities, and isotropies, heterogeneities. So we have to develop generally specific numerical approach, since the conventional numerical tools pains in some cases to provide accurate solutions in reasonable computing times, which is not compatible with, for example, sizing or an optimization process. Here I present some of our works done in this domain. In this work we have studied pulse eddy current testing to characterize thickness and conductivity of conductive plates. We considered different plates with different thickness and conductivities, and we used numerical modeling to model the system of coil above this plate. We have noticed that the conductivity of the plate affects mainly the zero crossing time, and the thickness of the plate affects the magnitude or the maximum of the eddy current variation in the probe. For experimental realization, we had problems we had not material to apply such voltage signals. So we have used Fourier reconstitution of this signal, and we apply different an alternative, yes, sinusoidal sources with different frequencies to reconstitute this signal and the current due to each harmonic. Okay, the part of the current due to each harmonic of the voltage is we divide the harmonic of the voltage by the impedance, taking account of the variation of the frequency, and we shift it in time here. In this work, we have considered an array eddy current sensor to characterize flows, cracks in conductive materials. It's a 3D problem, very complicated to model in 3D. So we developed a modeling approach to avoid the 3D approach. We by doing just an axisymmetric modeling of a coil above a plate, conductive plate, and then we reconstituted all the source files created by the coils by moving the placements of the coordinate of the coil. So we have the source file created by all the coils in the tested material. This source file is used to as a source in an integral equation involving dyadic Green's functions to compute the effect of the crack, which is represented by an electrical dipole that cancels the normal electrical field on the crack. Electric current cannot flow through the crack, so the normal component of the eddy current is nil on the crack, and this is achieved by this equation. We represent the crack by an electrical dipole here P that cancels the normal component on the crack instead of modeling the crack numerically. So, because if you model the crack numerically, you have to mesh the crack, you have to put a very thin mesh in the crack. So it's singularity. The crack is supposed to have no thickness. Yeah. For the inversion, we considered the crack as an array. The crack is, instead of looking to the exact shape of the crack, we represent it in a discrete form like this. It's represented by an array. This array will have the number of elements of the array is a discretization in this direction, and the value of each element of the array is a discretization in the other direction, this way. And we used a genetic algorithm to compute to reconstitute the shape of the crack based on the measurement on the impedance variation in each coil here. I can explain more if you want after. Here, no, it's not this one. Here we have considered eddy current testing of composite material, CFRPs, carbon fiber composite, carbon fiber, reinforced polymers. Thank you. Reinforced polymers. These materials were used in the fuselage, in the new plane fuselage. It's a multi-stack material constituted of what we call plees. Each plea is constituted of carbon fibers of about 10 micrometer in diameter. So we have in a plea about 10 fibers here. Please is about 100 micrometer. It's an heterogeneous material and an isotropic material. We have the conductivity and the direction of the fibers is very different from the conductivity in the transverse direction. Here we have some values of typical conductivities of these materials. These conductivities depend obviously on the fibers. Volume fraction, this is what I say. The fibers volume fraction in the material. Here we have the conductivity tensor of one plea, and when we have a multi-stack, if you consider an external reference, coordinate reference, you have this conductivity tensor taking account of the direction angle of each plea in the tested material. We have developed integral differential models to model eddy current in such material to avoid matching the surrounding air. We discretize only the active part here. We start from the conservation. Sorry, there are some equations I like to explain little what are present here. We start from the electrical current conservation. The electrical current is conserved in the system, so the divergence of the electrical current is 0. So we derive the electrical current from a curl of a potential, an electric vector potential, since the divergence of curl is nil. Okay. Then we divide here the magnetic flux density into its source and reaction term. The source term created by the source part of the system, a coil, if you put a coil above the tested piece here, and the reaction part due to eddy current here, BR. We use Biot-Savart formula. It's a Biot-Savart formula to compute the source and reaction term here. In Biot-Savart, this formula involves the source current and the reaction current of the tested piece here, which is presented by a curl, the curl of the potential vector T here. From Maxwell-Faraday equation, the curl of B minus the derivative of B. Okay, you put it here. Okay, you have this from this equation. You have this integral differential formulation of the problem. The impedance variation of the coil or the sensor is computed like this. It's the product of the current, the source and the induced current in an integral equation. To avoid, we have here integral equations that are full or in the best case are very dense. So to avoid to invert these matrices, the matrices generated by these integral equations, we adopted an iterative solving of the matrix system resulted in this equation. We start by taking only the source term, which is calculated by the source current here. So we put the curl, this matrix is the curl matrix, resistivity matrix, curl matrix, curl R, curl T0. T0 is the potential, electric vector potential at the starting, the zero iteration. Zero iteration. We consider, in this iteration, we consider only the source file, the source field. Then we compute, from this we compute eddy current, the curl of the potential vector here. Then we compute the new value of the magnetic flux density with considering the reaction term here. Then we solve again this equation by the new value of the magnetic flux density, and we proceed iteratively until the convergence criteria that you want on G or on T. Here we have also, based on this numerical modeling, we have developed rotating eddy current sensors. It's a new configuration of sensor that can allows us to characterize the fiber's direction in a multi-stack, in a multiply composite here. Here we, in this example, we considered a CFRP with 4 pleas oriented in the direction 0, 90, minus 90, 44, 45, 90, minus 45, and so on. So you can recognize here the response of the eddy current sensor due to the presence of each plea. And you have here the eddy current flowing in each plea of the multi-stack here. We have also developed characterization methods of this type of material based on resonant circuits. We found that the resonant frequency are very sensitive to the variation of the conductivity, and here we have a plea, single plea, put in a gap here of a resonant circuit formed by a ferrite core. It's a ferrite core that we cut in this direction with a rectangular section ferrite core. We want a coil here on the ferrite. We put the whole an impedance analyzer. So we measured the variation of the impedance of the ferrite core here with respect to with varying the plea in the ferrite core. This is the response. You have here the response when the fibers are in these directions, and another response for when the fibers are in the perpendicular directions. So this is used also to characterize the conductivity. Conductivity is parallel and perpendicular to the fibers. This modeling has been adapted. This type of modeling has been adapted to model composite superconductive materials, composite types, which are constituted of high temperature superconductive material embedded in a conductive matrix. The structure of this composite types is similar to the CFRP, so we used the same approach to model such materials, with including here is the same iterative approach for solving the matrix equation with an update. Since the system is nonlinear, we update the value of critical current that depends on magnetic field and the conductivity that depends on the critical current. Maybe, I don't know, maybe I gave little description for superconductive material. In a superconductive material, the conductivity is nil under a critical temperature. And the electrical field in the material is the relation between the electrical field and the electrical current density is nonlinear. It's nonlinear. It's generally given by the exponential power law, the power law given here with a variation of the critical current, which depends on magnetic flux density. So our works are going are carried on this application. So I have finished my talk. Thank you for your listening, and I will be pleased to try to answer your questions if there are any questions.
Thank you, Oisin, for this interesting presentation with a few equations, that's for sure. I think we're going to move in 5 minutes to the other talk. You can keep the questions for the round table. We have a round table at the end of the session. So that will give you the time to think over the questions you have for Professor Oisin. And we have 5-minute breaks. So you can rest a little bit, and we see each other in exactly 5 minutes to go for Loic's presentation on superconducting levitation. And after we have a small round table, already said it, for half an hour, so you have plenty of time to ask questions at this moment. Thank you very much.
Ok. Désolé, j'ai dû improviser sur certaines parties. Hein. J'ai pas eu le temps de...
C'est pas grave, il n'y a pas de souci. Et après, tu vas voir les questions à la fin.
Ouais.
5 minutes.
Non, c'est vrai.
Ouais, j'ai qu'on a...
An hour or so.
Mais c'est ce qui était prévu au départ.
Non.
Non. T'avais dit 1 heure. T'avais dit 1 heure, 45 minutes de speech. Non.
C'est fort.
Attends, je te remets le mail. Tu vas voir.
Je sais pas pourquoi tu te préoccupes. T'es passé. Il n'y a plus à te préoccuper, c'est à Loïc maintenant.
Non, c'est-à-dire si j'ai pas bouffé ton temps.
Non. Loïc va rattraper.
Tu vas rattraper quoi?
Le temps perdu.
Le temps, on peut pas rattraper. C'était bien. Enfin, moi j'ai appris. Moi j'ai appris plein de trucs.
Ah, c'était le but, en fait.
Faudrait que je te montre un truc que j'avais fait en master. C'était du MDT. Et enfin, je crois que ça rentre pas dans une des catégories que tu as mis. Ça dira s'il y a moyen de faire un truc.
Pourquoi pas publier un truc.
Parce que c'est un truc qu'on n'a pas publié parce qu'il manquait d'expérimental. Mais au niveau de l'idée, c'était pas mal. Quand on a fait un peu d'expérimental, mais j'ai développé.
On en discutera.
So you sit between you. You can sit at the end so you can talk. Okay, so we're going to resume the activity, the second talk. So I'm pleased to present Dr. Loïc Keval from Central Supélec. In 2010, he studied his PhD at the University of Tokyo in Japan. He completed the PhD in 2013 on superconducting machines. From 2013 to 2015, he did his postdoctorate at the University of Applied Science at Düsseldorf in Germany on motors for electrical vehicles. Since 2015, he's at the Group of Electrical Engineering of Paris at Centrale Supélec, working on HVDC development, this kind of system for the power grid. So, Loïc, please, this is your turn.
Thank you.
Thank you.
Good morning, everybody. Thank you, Frédéric, for inviting me. Thank you for the support of UNAM, and thank you to all of you for coming and staying here. I hope we will have a good lunch after. Okay, so as Frédéric told you, I'm with the GIPS. This is a lab of electrical engineering near Paris. So the P is for Paris. And it's supported by 4 institutes, 4 universities, and I'm working for this one here, Centrale Supélec, and I'm mainly teaching electrical machines. As far as the location, it's near Paris. It's like about 30 kilometers south of Paris. Okay, so you are free to come to visit and test some food. So this is a big lab, and actually the lab is divided into smaller groups, and I'm part of this group here. Inside GIPS there is this group, System, and we are covering all these applications. So this will be actuators and sensors, so machines. This will be microgrid, power electronics, power networks, integrated circuits, and electrical discharges and arcs, okay? And I'm more involved in that group here, electrical power networks, and especially HVDC applications. So this is DC grids, high voltage. Concerning some collaborations, so I'm here because we are in collaboration with a group of Professor Trio about superconducting components for the grids here. And the work I'm going to present today is something that we just finished. It's like 2 years old. And it was a collaboration with KIT in Germany and Southwest Jiaotong University in Chengdu in China. And so I thank my collaborators for their support and all the work that's actually inside this presentation, and that it's a lot of work, okay? So this is the outline of the presentation for today. I'm going to do a very short introduction about superconductivity so that we know what we're talking about. And then we are going to talk about maglev vehicles, and especially superconducting maglev vehicles. Okay? And then I'm going to show you really quickly what we do in my lab about modeling and optimization of this kind of system. Okay? How you in research, help to develop this kind of system. So, let's start with a short introduction to superconductivity. First of all, what's a superconductor for you? What's a superconductor?
Small resistance.
Okay, so I'm hearing small resistance, okay? Zero resistance. It's usually what you think about when you think about superconductivity. You think about perfect conductivity, zero resistance, okay? This property has been discovered in 1911, so it's more than 1 century old, by Hans in Netherlands, okay? And this is this name because it has zero resistance, perfect conductivity, that we call it superconductor, okay? It's based from that. Is that all? Of course, we have some space here, so it looks like there is another property. What do you think? Another property for superconductor. If you don't have this second property, you are not a superconductor. Something related with magnetic fields. Doesn't penetrate the conductor. It's called Meissner Effect. So when you're in normal state, when you have a normal conductor, the magnetic field is penetrating the conductor will be the red part here, and when you are in the Meissner state, the field doesn't penetrate the superconductor, it's expelled, okay? Let's check a small video to see that effect.
In this demonstration, the black object within the styrofoam container is a single-grain yttrium barium copper oxide high-temperature superconductor that is specially made in our own laboratories. Located next to the superconductor is an iron spoon. In normal room temperature, superconductors act like stones, having no interactions with the spoon whatsoever. This round object with a metallic luster serves as a powerful magnet. When the iron spoon is placed close to the powerful magnet, the magnet is rapidly attracted to the spoon.
Okay, so here, right now, I have a superconductor here. This one is IPCO, it's one type of superconductor, and it's at room temperature, it's not cooled down, so it behaves like a stone, okay? And he put a permanent magnet here, and he put a spoon, and you see that there is an attraction between the permanent magnet and the spoon, of course, okay? Now what he's going to do is going to cool down the superconductor, and I like this video because you are going to see how much time it takes to cool down the superconductor so that it becomes superconducting. And you will see it's not so complicated.
The smoking liquid that is being poured out on the superconductor is liquid nitrogen. Its temperature is 196 degrees below Celsius or 77 degrees Kelvin. The liquid near the superconductor undergoes intense boiling due to the heat that the liquid nitrogen absorbs from the superconductor.
So here you have bubbles, it's boiling.
Liquid nitrogen becomes nitrogen gas, and the temperature of the superconductor drops gradually. When the boiling ceases, it indicates that the superconductor and the liquid nitrogen are in thermal equilibrium. This indicates that the temperature has cooled below the superconducting critical temperature, or 91 degrees Kelvin for the yttrium-barium copper oxide compound, and has established superconducting properties.
Still boiling. Let's wait. When there is no more bubble,
in the process of cooling,
it's at the same temperature of the liquid nitrogen, 77 Kelvin.
We call this cooling condition zero field cooling,
now it's superconductor,
which means the
not
superconductor is cooled with no outside magnetic field influence. After the superconductor has established superconducting properties, as the magnet approaches the superconductor, a strange reaction occurs. The superconductor is repelled. This effect is called the Meissner Effect.
Okay, the field cannot enter inside
Now
the superconductor. Meissner Effect.
In place by pushing.
And actually, even when you push, there is a strong force because the field doesn't want to enter in the superconductor. Okay, actually, it's even more magical. If you cool down the superconductor, if you put this liquid nitrogen, you cool the superconductor, but there is already an external field. You are already near the magnet. Actually, this field will be expelled from the superconductor. This is even more magic for me. Okay, so it's not only that the field doesn't enter. It's like if there is a field inside, you cool it down, and during the transition, you push the field outside. This is the Meissner effect. Okay, so is that all superconductivity? There is a small tips here. Is that I wrote type 1. So if there is a type 1 superconductor, of course there is a type 2 superconductor. So this one is a little bit more tricky. A type 2 superconductors, it has the two first property, perfect conductivity, Meissner effect, but there is another state which is called mixed state, and in that state you have something that we could call flux trapping effect. So actually in between the normal and the Meissner state, the flux can enter one by one, quantized effect, inside the superconductor, okay? And this works only under a given field, and this is called critical field, HC or BC, okay? And this critical field here depends on the temperature here, so it's a little bit complex to explain how it works, okay? So if you want to be superconducting, you have to be behind this field and behind this temperature. Here inside, if you are more field or more temperature, you are not superconductor anymore. This effect here, it has been discovered in 1933, so it was like 22 years after the discovery of zero resistance. Okay, so it took some time to understand what was a type 1 superconductor, and then even more time to understand what's a type 2 superconductor. And to be honest, even today we still don't know really how works a type 2 superconductor. If you find how it works, you can win a Nobel Prize. Okay? So, as I told you, if you want to be superconductor, you have to be under a given temperature, you have to cool it down, you have to be under a given field, here. And actually the field depends on the applied field, the external field, and depends on the field created by the material itself, okay? It's superconductor, so you can have a superconducting current. This current is creating a field. So the current inside the material and the field, they are related, okay? So if you want to be superconductor, if you want to be inside, you have to be under these three numbers: critical temperature, TC, critical field, HT, and critical current density, GC. Okay, very important. You as electrical engineer, if you want to design an application where you use a material as a superconductor, you have to make sure that you always stay inside this volume all the time. If you go outside, you lose superconductivity. Okay? We are going to talk about maglev application, so a train. If you lose superconductivity, you lose levitation and you crash. Okay? So we have to make sure that it always works. Okay. Small history of superconductors, just to remind you a little bit. The first one discovered was this one, mercury, in 1911, okay? This is with this one that we saw that we have zero resistance, okay? And then, a lot of research, and we found like other superconductors that have higher critical temperature. So it means you need less cooling power, so it's easier to use, okay? And the goal is to go here as high as possible, if we can, room temperature, so that we don't need any more cooling, okay? As far as today, the highest room temperature, the highest superconductor, the highest TC that we found, is this one here, at ambient pressure, okay? This is 138 Kelvin, this one. And if you put pressure on the superconductor, you can go a little bit higher, this one, or you can go even higher. This one has been discovered, I think, last year or 2 years ago. Hydrogen sulfide, but you need 155 gigapascal. It's huge, so it's going to be super difficult to use. But still, look at this temperature. It's only minus 70 degrees Celsius. Only minus 70 degrees Celsius, okay? So it starts to be interesting. The same thing, if you find a superconductor here that works at room temperature, even if you don't know how to explain it, you can win a Nobel Prize. So, we are electrical engineers. So we want to use superconductors, so they have to be fabricated as tapes, okay, conductors, so that we can do machines, anything. This is a conductor that you can buy. They are commercially available. You have this first one here, 1962. It has been available since a long time here. It's niobium titanium. Very common, good electrical properties, good mechanical properties here. And this is this one that you mainly find probably 99% of the application today, especially MRI in the hospitals. You have this kind of conductors, this one. Then in 1986, we discovered what we call high temperature superconductors. So it means the TC is higher, more than 35 Kelvin. And right after, this one and this one, they could be manufactured as tapes, okay? Actually, this is this one here in 1988 that was manufactured as a tape first. So that's why we call this one 1G, okay? And we call it BISCO. Okay, so it's good to remember. And then, a little bit later, this one, it was manufactured. So it was discovered a little bit before, but it was manufactured as tape a little bit after. So we call it second generation, okay? First generation, second generation, and this one we call it IPCO. Okay, and you can buy it right now. And recently, 2001, Japanese team, they discovered actually the material, and they could manufacture quite quickly, it's been only 15 years, conductors, we call it MGB2, okay? And it's commercially available already kilometer lengths. So it's something interesting. This one and this one, they operate at quite low temperature. This one is less than 9 Kelvin, this one less than 39 Kelvin. So it's quite cold, but they will probably be used for the same kind of application. This one is more higher temperature, it's like around 100 Kelvin. So it's a little bit easier to use, okay? The one we saw in the video was this one, IPCO. But not as a tape, but as a bulk. So a bulk is like a permanent magnet, okay? So you can fabricate a tape with your superconductor, or you can fabricate a bulk. You can fabricate a cylinder, you can make plates. For example, here, what we did was to put plates, joint one with the other to make a bigger superconductor here. This is a magnetic shielding, and you can even have like strange shapes like these hollow cylinders, okay? And you can use it for your application. All this is IPCO, okay? And this is actually this one that we are going to use for magnetic levitation. this kind of material as bulks. Some application today of superconductivity. So you all know MRI. This one is one of the latest MRI available, 3 Tesla from Siemens. Okay, so it's really nice products you see everywhere. Another application, some physics experiments, especially Atlas experiments made with superconductors. So actually these 2 applications, they are really specific. They correspond to applications where conventional conductors, like copper, aluminum, wouldn't work so well. Okay? So it's kind of a niche market. Okay? Because here, you will need a really large coil all the time. It will cost a lot of money in your hospital, a big electricity bill. So superconductor is a good idea. Here you need really high field, high stability, really difficult with a copper. Superconductor is a good option. So it's a good way to think. If you have a niche application, a market, a small market where conventional conductor doesn't work that well, maybe it's good for superconductor. If you are in competition with conventional conductor, it's going to be more difficult. Okay, because conventional conductor is just less expensive, easier, no cooling. So let's look at some application of tomorrow. This is my guess, okay? This is my guess. This is short-term application, mid-term application, and long-term application. What we already see almost available on the market, cables, AC and DC cables, fault current limiters, probably the first commercial application of superconductor in the energy market. In the industry, I think induction heater is going to pop up soon, and we already have MRI and NMR. Okay, we already have that, superconducting. And for science, magnets, Atlas experiment, for example. In the mid-term, I bet on superconducting wind turbine generators. That will be a wind turbine generator here. The reason why we always want to increase the power of machines, but this machines is at the top of a big mast, 50 meters, 70 meters. A big machine is really heavy, big tower. If you make it floating, it makes it complicated. If you go to superconducting machines, you can obtain a small machine, really lightweight. Okay, with a conventional machine, it's big, so it's difficult. I think probably if you go more than 15 megawatts, you will probably go for superconducting generators. So it's a good, probably niche market. Okay, and then maglev. So you have, for example, the Japanese maglev train. It's still a prototype, but it's being developed. Commercial operation very soon, 2027. So this is like midterm, 5 to 10 years. Okay. And then maybe longer term, maybe aircraft propulsion, magnetic separation, I think a little bit longer term. Okay, a lot of work to develop this kind of applications, so I count on you. Okay, now we all agree what's a superconductor, 3 properties, zero resistivity, Meissner effect, and in between mixed-state flux trapping effect. Let's talk about maglev vehicles, and especially superconducting maglev vehicles. Those are 3 maglev trains, Maglev Technologies, okay? Question, which one is superconducting? Which one is superconducting? So?
I took the train.
This one, is it superconducting, this one? This one is the one in Shanghai between the airport and the... Is it superconducting? I think it's not superconducting.
No, it's not.
Is it superconducting, this one? Actually, this one is superconducting. But it's not superconducting magnetic levitation. It's another kind of levitation. But it's superconducting. But you don't need superconductivity to operate. Let's discuss that later. And this one, the Maglev Cobra, is a superconducting train as well. Okay, so you have here this one and this one, they are superconducting trains. They use superconducting components, but maybe they don't need superconductivity to operate. Okay?
I took the train, I took the Cobra.
This one?
Yeah. It's 100 meter long.
Yeah.
And it's smooth. I mean, I took it, it's real. It's not just an image.
So why is it good for you, Maglev Technologies? We already have trains, not so much in Mexico, but still. Why is it good for you? What kind of advantage do you see?
Faster. They can travel faster.
Why faster?
Because there's no friction.
Okay, there is no friction, okay? Between the rail and the train, there is no mechanical contact. It's levitating. So there is no friction, so you can win speed. You win that. Less friction means faster. It means less consumption and less noise. Okay. Other added advantages: you can have higher gradients, smaller turn radius. It's quite useful for some applications. Okay. So this is one of the reasons we are developing maglev trains for different applications. This one is actually for subway applications, like city application, and this one for long distance applications. Okay. So now actually in Maglev Technologies, you have three kind of levitation technologies, and the goal, your job, is to tell me which one is transrapid. Is it electromagnetic levitation? Is it electrodynamic levitation? Is it superconducting magnetic levitation? Which one is it? So it's not superconducting. So it's this one or this one.
What's the difference between electromagnetic and electrodynamic?
So this one use electromagnets, and this one use electromagnets but with induction, and you need to move. You need to be dynamic. If you don't move, you don't have levitation.
That means you have an electrical field to give the force, no?
Yeah. So the transrapid here.
Electrodynamic levitation on my side.
What's your bet?
Who agrees?
Okay, so the solution is EML. It's electromagnetic levitation. So actually, how does it work? On the track here, it's a passive track, okay? And inside the train, you have electromagnets. The electromagnets, they are actually here, under the track, here, okay? You power the electromagnets, you get an attraction force, so that you can lift up the train, okay? So you need an electromagnet, and it's attraction force, so it's unstable. Attraction is unstable, okay? So the levitation gap is 8 millimeter for the transrapid, 8 millimeter, okay? And the maximum speed is 550 kilometers. For commercial operations, 505 kilometers. 500 kilometers, 8 millimeter levitation gap. I think you can realize the challenge, the technical challenge it is to correct, because it's unstable. So you have to be able to control, detect and correct in less than 100 milliseconds any modification of the air gap, okay? German technology, they did it, but quite complicated. So the maglev train developed in Japan, this one, the GR maglev. So you have only two solutions, electrodynamic or superconducting. This is a superconducting train, but it doesn't mean that it needs to be superconducting to work. So which one? So it's EDL. It's a little bit easier because you know that this one is superconducting. EDL. So EDL, what does it mean? It means that you are using electromagnetic induction between a superconducting magnet that's on board the train. So inside the train, this part here, here, and here, it's a superconducting magnet. It creates a DC field, a huge field. That's why we use superconductivity. And here, you have a U-shaped track with copper coils. When the magnet moves, induction, you repel. It's a repulsion force, so it's unstable too. And you can obtain levitation. So it's induction effect.
So you have to have an electrical field, a wave electrical field to move.
A wave, yeah.
Induction because you have to move.
So the train is already moving with another motor, with a linear motor. Okay. So if you don't move, you are not levitating, because induction, it's only when you have a modification of the field. Okay. So if I have my DC field in the train with my magnet, but I'm not moving, I'm at the station, the train doesn't fly. Okay. So it means that this train at the station needs to have small wheels. Okay. So if you enter the GR maglev, when you're at the station, you are not flying. It has small wheels on there. And when you go over 100, I think it's 120 kilometers per hour, it starts flying. Okay? And both the levitation and guidance force, they are provided by this induction force here, and that's why you have a U track. It's like a U shape. Huh? Okay? So, some interesting numbers. This is this train. I mean, you can call it a train if you want. That has a world record for speed, 603 kilometers per hour. Okay? I think the French TGV is not so bad because it's a conventional train, 574 kilometers per hour. It's not so, only 25 kilometers less. I think we did a good job with wheels. So this one is the fastest. For commercial operation, it's planned to be 500 kilometers per hour. They started the construction for the commercial application. They started 2 years ago, 2015, 3 years ago. They are going to connect Tokyo to Nagoya, so it's 350 kilometers. And they think it's going to be finished by 2027, maybe before, because of the Olympic Games, so the government is pushing for that. So 350 kilometers in 40 minutes. In 300 kilometers, where can you go from here, from Mexico? Acapulco? So you could go to Acapulco for 40 minutes. Huh? If you have 2 hours break, you can go to the beach and come back.
Yeah, that would be nice.
Okay.
They teach at the beach as well.
40 minutes, you just take the train. So this is for 2027, and then, if it works, they are going to make the line longer. They are going to connect to Osaka. Tokyo, Osaka, it's 500 kilometers. Where can you go 500 kilometers?
500 kilometers? It's Guadalajara. About that?
Yeah, Guadalajara.
On the coast as well.
On the coast, okay, and the connection is going to take 67 minutes, so it's 1 hour and 7 minutes, 500 kilometers, okay, and they plan that for 2045. They plan to operate 8 trains per hour in each direction, so it's it's one train every less than 10 minutes, so it's like a subway, but they already do that with a bullet train, so there is no problem. And each train is going to carry 1,000 passengers, okay? So it's a lot of people. Construction cost. This is a nice statistics. 90 billion euros. It's 1,800 billion pesos. 1,800 billion pesos.
How does that compare to a project, let's say, even Moscow?
There is no communication about the price of Hyperloop projects, so I have no idea.
Yeah, but that'd be interesting because, of course, it will sound ludicrously expensive, but if you compare to the cost of, say, any...
Exactly.
Probably that's cheaper.
And you have to think about something, is that this is the cost of this project, because they are going to install a train in Japan where they have a lot of mountains. They are boring really deep inside the mountain. It's really like big mountains. So biggest part of the project is actually only to make the tunnels. So we don't really know the price of the train per kilometer. We kind of are overwhelmed by the price of the tunnel. So it's really difficult to know the actual price of the technology. They are going to try to sell it to US. Let's see if it works, and maybe we will have a better knowledge of the price of the technology. So interesting fact, they plan the train company to spend all the money themselves. They are not asking for the government help. Okay? That's quite interesting. 90 billion euros. It's going to evolve with time, huh? But still it's really interesting. So the question is, you have these 3 kind of levitation technologies. Why did the Japanese choose this one? Why not this one? On the superconductivity, why not this one? Levitation gap. The levitation gap of this technology is 10 centimeters. 10 centimeters is huge. This one is 8 millimeters, okay? Why? They need large levitation gap because they have many earthquakes. If there is an earthquake, they have to have a large levitation gap to absorb and stop the train, okay? So that's why they choose this technology. They choose it in 1962, so it's been 55 years they are developing this, okay? And it's near commercial application. Last one, Maglev Cobra, of course. The last technology, superconducting magnetic levitation. In that case, it's superconductor, but you don't need a superconductor. You just need they just use the superconductor to have a high field. But if you find a way to have a field with something else, you can. In that case, you need the superconductor, otherwise it's not going to work. Okay? Let's have a look at the end of the video to understand how it works.
It's good because they want to apply this Cobra, they want to have a line at Rio de Janeiro in the university.
Conductor is repelled. This effect is called the Meissner Effect.
Right now there is Meissner Effect, and he's pushing hard here because the flux doesn't want to enter. And he's going to push harder and harder and harder, and the flux is going to enter smallly, flux by flux, and is going to pass to the mixed state, okay?
Now we fix the bottom superconductor in place by pushing the magnet towards the superconductor. The magnetic fields from the magnet will pass through the superconductor, resulting in the so-called flux trapping effect.
Okay, we are in the mixed state here.
Now the superconductor and the magnet not only repel each other, but also attract. This combination of repulsive and attractive forces allows the magnet to stably float above the superconductor. This is known as magnetic levitation. If the magnet is slightly tapped, it will revolve above the superconductor as seen here.
Okay, you need a superconductor to do that. There is no way you can do that with copper or with really fast control system. So that will be, so actually in the train it will be reversed. You will have the superconductor inside the train and the permanent magnet on the track.
When we pick up the magnet, the superconductor will leave the container and be stably suspended beneath the magnet.
Magnetic suspension.
This is called magnetic suspension. Both magnetic levitation and magnetic suspension
so you can levitate the train or make it suspend
effect.
under the track. You choose.
When we forcefully separate the magnet from the superconductor and then slowly bring the magnet close again, the superconductor will be attracted by the magnet and be pulled closer. However, this reaction is not the same as two opposite poles of a magnet.
Okay, you got it? It was in flux trapping effect, so the flux was trapped. He forcefully separates them. When he brings them together, they come back together, but they stay at the same levitation or suspension gap. So this is really magical. If you do that with a magnet, conventional magnet, just have attraction and they touch together. Here they don't touch. There is some gap and that's fixed, okay? So you can imagine why it's good for a train, because you don't need any control, it's stable by default, and you have levitation controlled, okay? That's why they want to use this effect.
Magnet attracting and sticking to each other.
He's going to do it
the
all the
superconductor
time.
and the magnet both attract and repel each other, maintaining a fixed distance in between.
Okay. So this is this effect that we use in superconducting magnetic levitation. So you need the superconductor. Okay, so to do that, you need a superconductor. You will actually use the fact that it has superconductivity so that you can induce currents, and you will trap the flux to keep this gap constant, okay? So probably we are going to operate in this mixed state for a superconducting maglev train. So when I design the application, I have to make sure that I stay inside this. These are some prototypes. So you have actually 4 or 5 prototypes in the world. This one has a more advanced. The one in Southwest Jiaotong University in Chengdu in China here. This one is actually in a tube now. First generation was not in a tube. This one is in a tube. They are going to make the vacuum in the tube to operate without friction with the tracks and without air friction. Operation speed is planned to be 1,000 kilometers per hour. Okay. This is, and they are going to build, right now they are building a longer version with a big tube in a big lab, several meters long. This one is the Supratrans project. This is German project here. I think it's on hold right now. It's not moving anymore. And this one's the Maglev Cobra of Rio de Janeiro. Let's have a better look at the Maglev Cobra here. So this is how it looks like. We are using superconducting bugs, so it looks like this permanent magnet. We put the bugs inside the cryostat. This is the cryostat. Inside we put liquid nitrogen. Yes, this is this liquid that we put before. You put it in the morning, it's cooled down all the day, and the night you need to put more, okay? And this is a track with permanent magnets here. And this is a vehicle. They have here the cryostat, the track is under, and they have the vehicle here, and this is a mock-up vehicle. And this track, it has been built between 2 buildings at University of Rio de Janeiro, and it's connecting 2 buildings. And this is some photos.
Actually, it's to go to the cafeteria. That's what I took to get some sushi.
This is some video of the Maglev Cobra here, mock-up. So, sorry, Frederick, but you are not inside the video, so I'm not sure if you really took this train or not.
No, I'm going to send you the video when I took the train.
Look at that. Here, this is a linear motor. It's actually an induction motor here. Here, this is a magnetic track with permanent magnets, and inside the train you have the cryostat with the superconductors. Okay, and they are going to show you a nice view of the levitation gap. It's about 2 centimeters for this technology, about between 1 and 3 centimeters, 2 centimeters probably for this one. See? And this is what they want to do. They want to use it to do a superconducting train inside the city, because Maglev, you have a lot of flexibility for bending radius and high gradients, so it's kind of a good idea. Besides, with this technology, you don't need any power for levitation, you need only for traction. Okay, with the other Maglev technology, you need power for levitation. This one you don't need. So when it stops, you are levitating and you don't consume anything. So this is the philosophy behind the Maglev Cobra. Okay. So I know that you are curious. So here is a look of what's really inside the Maglev Cobra. Here you have superconducting bulks here. You have an array of 24 bulks. This is the bulks here. Here you have copper for thermalization here, and over the copper you have liquid nitrogen, this liquid that we saw before, cooling down at 77 Kelvin. This one here, and this is the shape of the track. So you have neodymium magnet, so it's really strong magnets, and they are in flux shape geometry, okay, to obtain really large gradients of the flux here. So this is how it looks like inside. Okay, so I have 5 minutes now to show you what I do about this kind of tests. I work with modeling and simulation, and the idea is to simulate that so that we can be able to optimize it. So, as you know, when you want to simulate something, you need the equations. We start from Maxwell equations, and Maxwell equations, they can be explained, like they can be written in terms of several state variables, and here we choose H, okay, the field H. You can use other formulation if you want, okay? Totally works. And inside this here, you have this rho, and this rho for the superconductor is a nonlinear law that depends on G, GC, and EC and N. This has 3 parameters, and to make it even more complicated, these parameters, they depend on the applied field amplitude and the applied field angle. So it's really nonlinear system, it's a little bit complicated, okay? So for you, what you have to remember is that I want to simulate a superconductor. I use Maxwell equations. Here I use these state variables, and this is my constitutive law. Okay? And you can choose another formulation if you wish. And so this is what I need to simulate. This one is a cross-section of the supratrans vehicle. So this is a German project, okay? This is what they have inside the train. This is the superconductor, and this is the track. Okay? So I have to simulate the superconductor, it's already complicated. Then I have to simulate the guideway. Inside the guideway I have permanent magnets. With the H formulation it's difficult to simulate. I have to simulate the exact geometry. See, you have like small corners here and here and here. And you have iron. This piece and this piece, they are iron. They are saturated, so I have to take into account the nonlinear relationship. So that makes complicated problem with the superconductor. Alone it's not complicated, but with the superconductor it's complicated. Then, if you have that, you have to simulate the bulk in 3D if possible. You have to simulate a movement between this piece and this piece. So that starts to be really complicated problems. And to finish, actually, with a small number of elements, like 1,000 elements in the superconductor, it takes already 1 hour to solve. Okay? So that's a complicated problem. Okay? So this is what we proposed. We proposed to divide. We simulate this, and then we make a coupling. So we simulate first this with a conventional formulation. In that case, we use potential vector A. This is the most conventional formulation to solve magnetics problem. We solve one static problem. Okay? So that's easy. So we solve all these problems in one turn. Then we solve only the superconductor with a small layer of liquid nitrogen around it with the H formulation so that we can reduce the number of elements, so that we can keep the computing time low. We need a coupling between this model and this model. This is a field created by the permanent magnet. This is this field. And this field, H self, is a field created by the supercurrent inside the superconductor. You have supercurrent inside, so you need to apply it on the boundary again. Okay? So we simulate only once. Then we use this as a coupling, and we simulate the H formulation only once. This one is static model, this one is dynamic model, and to simulate the movement, we just change this as a function of time. We just make it move geometrically. So this simplify the problem. So this is what we do. We divide and then we simulate. When you make a model, it always works. Okay, so that's not why it's true. You have to validate it, really important. Modelization, validation, and then maybe you can use it. Validation is here. This is my system. I simplify the problem. I use a permanent magnet like this. I use a superconducting bulk like this. Two really simple. I put them in this machine. This machine is moving the superconductor in that direction. Of course, the superconductor is cooled down with liquid nitrogen, and I'm measuring the force between the two. Okay, only in the vertical direction. And this is here, what's happening. Look only at this part here, only this part, please. This is your initial condition, I'm far. I'm going to cool it down, so I'm going to put the liquid nitrogen. Now it's cooled down, so it's superconductor. Then I'm going to move it down and then move up. I move it down, and then I move up. Okay, and when I do that, I measure the force. This is the levitation force here. And the measurements, this is the dot, and the simulation with the 2D model is the line. As you can see, really good agreement. It's actually really difficult to obtain a nice hysteresis loop like this, so you have to have a nice calibration. When you make a validation, don't do only one, do several, because you will see many problems. This is another problem, even more difficult to simulate. In that case, the superconductor is cooled down near the magnet, so you are directly in flux trapping effect, okay? So I'm going to cool it down here, I'm going to move near the magnet, move far away, and then come back to the initial position. And this is a comparison between measurement and experiments, okay? So once you have done that, you trust your model, you can use it for something, okay? This is 2D model. Actually, we did the same with 3D model and with 2D axisymmetric model so that we can simulate everything. For example, this is a validation for a 3D model. In that case, this is the permanent magnet track. This is the superconductor. The superconductor is moving both in this direction and in this direction this time, so that we have both levitation force and guidance force, okay? And this is the validation. Here I'm cooling down. I'm moving near. Levitation force is increasing, but no guidance force because I'm still at the center. Then I'm moving on the side, one side. I have some guidance force. I want to negative guidance force. It means the force in that direction. I want to come back where I was, flux trapping effect. Then I move in the other direction. The force is positive now. So it means it's pushing the bulk in that direction. I want to stay in the middle, so I'm pushing in that direction. And I come back in the middle, okay? And in that case, this is the agreement between measurement and simulation. As you see, this is a much more complicated system, so the agreement is not so good now. You have more degrees of freedom, but still you can move on, okay? Okay, once you have a model, it's validated, you use it for something, otherwise, why? Huh? So we use it for optimization. This was a 3D model, okay? The one that I showed you before. You want to optimize, so you want to move to 2D to make it faster. Here are two techniques to move to 2D. You can reduce the current density, or you can reduce the length in this direction. Actually, the blue technique works better. You have a better agreement between 3D simulation and the blue simulation, so two techniques to go to 3D, to go from 3D to 2D, okay? Then you optimize not for a given position, for a displacement sequence, okay? Because you want the train to fly, so on a given sequence. So this is what we did, and this is our optimization objectives. What you want is win money, yeah? You want to optimize to minimize the price of a permanent magnet guideway. Money is the most important here. When you do that, you want to add another objective, which is to maximize the lateral force, the guidance force, okay? Because you want stability. So you are going to choose something between the price and the stability. You don't want the train to go out of tracks. During the given displacement sequence, so we are going to use this displacement sequence, we have the cooling down, then we put people inside the train, so it goes near the track, and then we move on the side, because there is wind, because you have curves, so the train is moving on the sides of the track, so it looks similar to what I did before, to this simulation. So this is actually this sequence. Here, I cool it down, I put people inside the train, so it goes near the track, and then I operate the train, I move on the left, I move on the right because of the wind, because of the curvatures. So you need to take this into account. Why we need to take this into account? Because if we look at the levitation force, it was here when we cool it down, and because we move on the side, the levitation force is decreasing. So if you don't take this into account, if you don't take this displacement sequence into account, after one day, the train is touching the track. You are not levitating anymore. So you need to optimize that, okay? So this is why we choose that. And this is the results. This is your initial design. This design here, a little bit simplified to make it easier. This is the one that was optimized for the supertrans project, but without really taking into account this displacement sequence and the superconductor properties. Here, this is what we do. And here, all the blue dots, this is the optimized points. Yes, this is the Pareto front of the optimization. So what you can see is that if you are ready to pay the same cost as initially, the same cost, you can win some stability just by optimization. If actually you just want some minimal lateral force, which is that number, you can actually decrease the cost by 23%. Okay, 23% is a lot of money. A lot of money. This is the price, estimated price for 1 kilometer, about 1,000 euro per meter. So for 1 kilometer is 1 million euro. So if you win 25%, you win a lot of money. And actually, if you are ready to pay even more, you can have a really large guidance force, a lot of security guidance force. So this is why it's useful, this kind of model. Short conclusion, if you have any questions.
We're going to have a section of questions afterwards.
Okay, so thank you very much.
Thank you, Loic.
Thank you very much. So I think we're going to move forward because the time is not on our side. So I will ask the speakers to come to the stage. I will invite as well Dr. Cesar Monsalvo from UAM. This is part of our events on electromagnetism. We're going to answer a question, principally people who has given their talk. And we're going to discuss a little bit in general what are the ideas behind those kind of presentations, and as well why it's so important to study electromagnetism, to apply electromagnetism, to develop electromagnetic systems, and nowadays is something essential for engineers to have some knowledge about this field. Thank you. Okay, so if you have any questions, I think the speakers can answer now the questions you had in mind during their presentation. So, I would like first, if you allow me, Nasser, I would like first the students to participate. This is mainly for them. And if no one dares to participate, then I will give the word to our fellow colleagues. But it will be nice that some students can ask some questions. I'm sure you have some questions. I would be surprised that you don't have any questions for our guests today.
This is your chance of grilling a big fish.
Alejandro, please.
I didn't understand the suspension phenomena in the magnet and the superconducting bulk, so I'd like to hear.
So the short answer is magic. It's flux trapping effect. As I said, if you can explain it correctly, nicely, Nobel Prize. Okay. So it's kind of really complicated. If you want to think about something simple, think induction. Any current in the superconductor will oppose the movement that you put. Okay. So if you have suspension and if you want to fall, then you are changing the position. Yeah. So you have induced supercurrents that tend to oppose and to maintain the position. So it levitates, or in suspension. It's another way to see it.
Okay. Thank you.
I forgot to mention something before the next question. Dr. Cesar Monsalvo is from the University of Autonomous University of the Metropole, UAM, and is here as part of this series of events on electromagnetism. Just 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 to make sure that people understand your presence here. So another question, please. People that are studying power system engineering.
I have another question.
For the please.
Menana, I didn't understand the in the eddy current testing, the rotational of parameter that is T. Is the current density equal to the rotational of T? But I don't know what is T.
Curl of T.
The curl of the electric vector potential. T is the electric vector potential.
Okay.
Yeah. Thank you.
It's a little bit like B is equal to curl of A.
Okay.
It's the same for current.
Okay.
In this sense. Another question, please, the students. Nobody?
I think
yeah, there is someone that dares to ask.
Yes, my question is for Loic. Yeah. Is how can I calculate the length of the gap?
The length.
Or how is the relation? The limit between the superconductor and the
Are you asking about the levitation gap? How I choose it?
Levitation gap, yes.
How I choose it?
The length.
Yeah, the length.
How?
Okay, so it's as always, it's money. Okay. If you want more length, you just put more magnets or more superconductor, and then you can have a big air gap. But you have to pay a lot of money. Okay. And here, this is kind of the optimal length for this kind of application: 2 centimeters for not so big quantity of material. Okay, so it's money, it's optimization. As when you do optimize anything else, it's always money. Yeah, so, but you can have a really large levitation. When you are 10 centimeters above the magnet, you still have a levitation force, but it's really weak. So if you want to make a train fly, you will have to use a lot of superconductors or a lot of magnets. It's going to cost you a lot of money. So you want to be near the optimal point. The max levitation force, the max force, is when you touch, but you don't want to touch. So it's in between, okay?
Okay.
So it's in between.
Thank you.
I would like to elaborate on that question because I had it myself. So, yeah. So the question that I had is, what the air gap and what does the air gap depends? Is it the field intensity? Is it the material? Can you control it? Is it temperature? I don't know.
You can change the field profile inside the air gap. This is why the Supertrans project and the Maglev Cobra project, if you look at the cross-section of the magnets, they don't look similar. They are different. They have been optimized for the Maglev Cobra. So this is what you change. Yeah, you try to optimize the gradient of the field in the air gap and to have the max field there. So you try to optimize that, but the field decreases really fast. When you go far from the magnet, you have no field quite quickly, so no levitation force. So you have to stay close.
Yeah, thank you.
More questions from the students? Yeah, please.
I have a question about the eddy current characterization. I would like to know. I would like to know what is the typical size of your sensing coils and the size of the defects you can measure with your system.
Yeah, thank you. The size of the coils goes from 7 millimeter to centimeters. So, and the defects are. It's not. It's the thickness of the defect. When we talk about cracks, for example, the cracks don't have thickness, but in the length, the cracks are about centimeters, from millimeter to centimeters. Well, you haven't to. There is no direct connection between the size of the coil and the size of the defect you characterize. You manage it in your version technique. I don't understand. I don't know if I answered your question or not. So, the question, if I understand, is the correlation between the size of the coil and the size of the defect you need to characterize. No, this is the
Yeah.
yeah. Of course, you don't choose a coil bigger than the defect. The defect has to be bigger than the sensor to be more precise in your characterization. Yeah. And the size of the coils lie between some millimeter to some centimeters, depend on what you want to do with it. Yeah.
In the same line, about the cracks, what is about the sensibility respect the width and depth and the field magnet? What is the sensibility?
So, I don't understand the sensitivity of the coil. How to,
yes, sensitivity.
Yeah,
sorry.
Yeah. As there are more lots of parameters that affect eddy current sensitivity and robustness, because we have to ensure two parameters: sensitivity to the crack, to the defect, and robustness to the other parameters that affect the. It's not trivial. It's not. It's the inversion technique that manages this kind of. These things. Yeah.
Okay, and for example, this technique is just for metals. And what about with the ferromagnetics metals?
Yeah, ferromagnetics are conductive too. So we used to characterize by eddy current. Pipelines are iron cores. Yeah.
Okay. Thank you very much.
Railways. You're welcome.
More questions? No, I will leave my colleagues to bring up some questions. I know some are eager to ask for some answers. Enrique, please.
Thank you. I have many questions for both of you. Perhaps during lunchtime we can go through some of them, but to keep it simple. In your case, Ossine, you were mentioning one of your first slides, you showed a conductor with a strip of superconducting material, and then you showed flux lines going like that. So it gives the idea of the current flux lines, right? So they are distorted by the presence of the strip of superconducting material, right?
It was conducting, non-superconducting. In the first slides?
It was one of the first ones.
Is it possible to put on the presentation?
So I'm intrigued by this because if you can shape the field, this could have many potential applications. Very interesting, I think.
Yeah, that was for
motor. Yeah, that was in the motor.
No, it was in Ossine's presentation.
Yeah, but that was about the motor, if I recall. There was a pole and a magnetic field and a ring around it, no? That was this? Yeah. Yeah, I think this will.
Could we have
can we have the presentation put on, please?
Español, Frederic. Mejor que lo digas en español porque no te van a entender. So perhaps I misread the slide, but I think you have a conductor, which is, and then you have a strip of superconducting material around it, and then you have your magnetic flux.
I think you are talking about this.
Yes, that one over there.
This.
I'm talking about
Thanks, Loic.
So is it possible in your opinion?
It's a field modulation in space.
Yes. Yeah.
There. These two coils, superconducting coils, that create magnetic field, and a superconductive shield in there. So we have here a modulation, a particular modulation of the magnetic field in space. So we have monopoles in this way. We have magnetic field enters there, don't go to the other coil. It is shielded by the superconductive plate here.
But is it possible to create the shape of the magnetic field around this object?
Oh, what do you mean create the shape?
So you have a regular shape like that if you have a single conductor, say, and you have, but then you introduce this element and you can distort the field outside. And can you design the shape of the magnetic field?
I don't understand what design the shape of magnetic fields. Gave other number of poles, changing the number of poles, changing the orientation. What do you mean by?
Yes, instead of having, let's consider, for instance, the simplest case. You have a conductor, a straight conductor like that.
Yeah.
So the shape of your field is like
around,
around
the conductor.
So this is a very regular cylindrical shaped magnetic field, right? So if I introduce one of these tapes of superconducting material, can I rearrange?
Yeah, you will deviate flux line of magnetic field.
Instead of this cylinder, perhaps I will have something like that.
You will modulate the shape of magnetic field. Yes.
Okay.
The basis principle is that magnetic field do not enter the. You are in a Meissner case here. Okay. So here we achieve a modulation of the magnetic field, like you have two poles here, north and south pole, and the active part of the machine is here. Okay. Magnetic field comes from the coils there, and you use this part as inductor in a synchronous machine.
Thank you. I have a couple of questions. Can I? Or is there something?
Can I give the word to someone else and get back to you?
Nasser, please. You had a question.
Just a simple, obvious question for Loic. When I see all these magnets on a track, the first thing I think about is stray fields. Does that mean everybody loses their credit cards, and then when you travel at 500 kilometers per hour, do you induce huge currents in everybody's?
So I know that in the GR Maglev, because it's near commercial operations, so they have to take serious care about this aspect, stray field. So the field that the people will see near the track or inside the train. So they are taking care of that. And the way they are doing it right now is using a shield inside the train. It's a passive shield, of course. So it adds weight to the train. So they are going to try to optimize this so that the field seen by the passenger is as low as possible. So they are taking care of that, at least for the GR Maglev. In the case of the Maglev Cobra, I don't know what they did. I think maybe not so much.
I don't know.
Did they? So, Frederick, you rode the Maglev Cobra, yes?
Yes.
Did they ask credit card? Did they ask you to leave your credit card, to leave your keys? No. So probably they did some measurements, because they had to make it open to the public, so they had to pass some certification and safety tests. So I think they had to.
Yeah, I confirm. We had to pay for the meal, no? So we took the train, we went to the cafeteria, and I could pay. Oh, they could pay. I don't remember. I think they paid for it.
They paid
and I don't recall. But I had my credit card with me, and nothing happened.
But this is a serious concern. No? You have to take care about that. Especially, you will have a huge field. Especially in the GR Maglev, you have huge superconducting coils on the side, so like 30, 40 centimeters near the passenger. So they have to shield that. Probably you have the same kind of concern for inductive wireless charging of electrical vehicles. And usually what they do is the same, passive shielding on the floor of the vehicle so that the passenger doesn't see anything. So the same kind of idea.
Enrique, you had some other questions.
If I may.
You may, or you sure.
So, just another question in this case for Luc. In your problem, you have the magnetic material, which is cooled down, and then it's brought near the permanent magnet, and then you have this motion, and we could see how the force is decreasing. But is this going like that all the time? Or does it stay at some point?
Yeah. So actually, this effect, it has been demonstrated actually quite recently, like less than 10 years ago, by several teams. And actually, after something like 5 iterations, 5 movements on the sides, it stays quite constant. The levitation force is not decreasing anymore. It's linked with a repetition of the induced current in the superconductor. When you have a repetitive movement after the second period, the repetition of the current is the same. So it's not decreasing anymore, actually. So that's why it's enhanced to optimize only on one lateral movement, only one period. The second period will actually stay the same. They have really nice experimental results for the Maglev Cobra about that, and they show that after 2-3 periods, the levitation force is not decreasing anymore.
How do you deal with extra degrees of freedom? Because it's not just moving like that, probably it's also...
Thank everybody, please. Thank you very much. Have a nice day.
That's gonna cost you. Tu récupères ta...